Hello everyone, welcome back. So today in this video I'll discuss about the Carnot engine. So in this chapter we have already discussed about the work done in an isothermal process, work done in an adiabatic process, the relationship between pressure, volume, temperatures in adiabatic process. So all these things we have discussed. Now this video will specifically discuss about Carnot engine, which is a reversible engine and basically an ideal engine, and we'll discuss and we'll find out its efficiency of this Carnot engine. So this Carnot engine, for that we'll draw one graph. Let's say we'll draw one pressure and volume graph, and the graph is like this. So we'll explain step by step. First let me draw the graph. Show the graph. Right, so this is a graph which will describe this reversible engine. The process starts from, let's say, this position 1, and this is position 2, this is your position 3, then this is your position 4. Now from position 1, this is the initial position where the pressure is, let's say, P1, volume is V1, and temperature is T1. Then position 2, your pressure is, why it is T1, T2, I'll explain you. So this is P1, this is P2, this is volume V2, and this is temperature T2. The start stage, the pressure will be, why so we'll discuss. So pressure will become P3, volume V3, and your temperature will be T2, right? Sorry, this one is T1, this is T2. Now here at fourth position, your pressure is P4, volume V4, and temperature is T2. So this is your reversible Carnot cycle. So what are the these points 1, 2, 3, 4. So this is the beginning of our discussion. From here, the initial condition, her pressure, volume, and temperature. Let us analyze with an example where temperature T1 is higher, and let's say it's a reservoir, it's a high temperature, you can say surrounding, you can say like that. So here one cylindrical system will bring, and in this cylindrical system, this is your piston, let's say, and all the walls are adiabatic. These are adiabatic walls except the bottom one. So bottom one is a isothermal, and heat, if I'll keep it here, heat can go inside, heat exchange is allowed, but not through other walls, only through the bottom heat can go in and come out, right? So when I'll keep it on this reservoir T1, which is a high temperature, let's say temperature T1. So when I'll keep it, it will receive the heat energy from this one, and isothermally I'll expand it. So it will gradually expand. This piston will go up, volume will increase, work will be done by the gas. Remember, all these lines are very important. Work is done by the gas. So gas, whatever energy they are acquiring, internal energy will change, they will vibrate, randomness will increase, so they will do some work and it will expand gradually. Fine. So when it will expand, it will do some work. We'll calculate the work done, right? In the previous video we have already discussed the work done in adiabatic and isothermal process. I'll repeat that. So here the work will be done isothermally and it will expand, the volume will increase. Now I'll bring this system and I'll keep it on an adiabatic stand, you can say. I'll keep it and I'll allow this piston. I'll first keep it and I'll allow the piston because the molecules are random, and this gas molecule, they will push the cylinder further upward direction, and volume will further expand, but not much. Here the volume will expand much, here the volume will increase, less amount of volume will increase here, right? And when I'll keep it on a adiabatic stand, what will happen? No external heat I'll supply in second case. This is the process from 2 to 3. This is the first. Isothermally I expanded, volume is increasing in x-axis. I have kept volume x-axis, so here volume is increasing, and temperature remains constant because here isothermally the expansion is being done isothermally. So temperature constant, volume is changing, and volume is increasing. Now your 2 to 3, the process 2 to 3, you see here the volume is not increasing much, right? But temperature is changing from T1 to T2 when there is no external heat I am supplying, and I am allowing this piston to expand by the internal energy of the gas. So here the expansion is done by the gas. So work is again done by the gas. Remember, here also work is done by the gas, here work is also done by the gas. By and on will do it. When we will find out net work done, that time we'll use it, right? So this is very important. So here also work is done by the gas and expansion is there, volume is increasing. So this first case and second case, here it is work is done isothermally, but here work is done adiabatically. Fine, because I'm not providing any external heat to the system, and all the walls are now adiabatic. Heat cannot go outside, neither heat also cannot come inside also. So here in this case the work is done adiabatically, expansion, the work done, that is adiabatically. So temperature is changing from T1 to T2, volume is changing V2 to V3, but volume will not change much. Fine. Now step 3 to step 4, what I'll do, this one is now allowed to expand, and when it will expand, the temperature will it will get the temperature, become the temperature T2, temperature T2. So T2, basically when it is expanding, temperature will fall down. So basically cooling process is being done. So gradually temperature is reducing in the system, right? So it will attain the temperature T2. Now I will keep it on another reservoir which is maintained at temperature T2. I'll put this system on this reservoir, and now it will again become isothermal process. And what I'll do here, I'll compress it. Now this reservoir is having this system is having temperature T2 after the expansion. Now I'll bring and put it on T2, right? Then I'll start compressing. When I'll compress it, what will happen? If it is adiabatic, then generally temperature increases, but it is now isothermal. So whenever I'll compress, gradually this system will reject the heat. It will release the heat to the reservoir. So reservoir will accept the heat because it is low temperature less than T1. So it will accept the heat released by the system, and but the temperature T2 will be constant, will be maintained because this is a reservoir T2. So heat exchange allowed, and here the system also will become temperature of T2. So I'll compress it. So here work is done on the system. Here I'm compressing it, right? Work is done on the system. Now the last case, that is your 4th to 1, again it will go back to its initial position, initial volume. So what will happen? Again I'll compress and I'll make its initial volume. So what I'll do, I'll just bring the system and keep it on again adiabatic, your so adiabatic stand. So this is your first case, this is your second case, this is your third case, and this is your fourth process. Fine. So again I'll keep it on the stand. So when I'll keep it on the stand, I'll compress it further, and all these walls are adiabatic. Remember, here also all these walls are adiabatic except the bottom one. Now when I'll keep it on an adiabatic stand, all the walls become adiabatic. Heat cannot go outside, nor the heat can come inside. So what will happen? External heat, I'm not supplying any external heat, so delta Q is 0, no heat supplied. So whenever I'll compress, then will be heat will the temperature will increase. So temperature will increase up to T1. I'll keep on compressing it till it attain a temperature T1 here, till it reaches the initial position T1, initial temperature T1, right? So this is my reversible cycle. Now for this reversible cycle, I'll calculate the net work done, in this cycle. Now I can also calculate the area, because I know that area under PV graph is also my work done, but I'll go by my previous results, that I have already calculated the work done for the adiabatic process and work done for isothermal process. Already I have calculated. So if you remember, so for isothermal process, the work done, isothermal process, the work done is, what is work done? Your W equal to, if it is expanding, then it is mu RT. Mu is a number of mole, mu RT ln P2 by P1. So this is your work done for isothermal case. If you want to convert it in logarithm, log base 10, this ln you will multiply 2.303, right? You can write in this term also, you can write 2.303 mu RT ln B2 minus log B2 minus V2 by V1 also you can write. And this is for expansion case, you remember, this is for expansion case. Here dV is expanding, so we are getting a positive work done. If it is a compression case, you will get a negative work done. So this is expansion case. Fine. So this is isothermal. For adiabatic, what is the work done? Work done for adiabatic is mu R in terms of temperature. Already I have done it. You can watch the video. It's in I think last week I have recorded, so it's there in the channel. You can go and search this video about work done in adiabatic. So it's mu R T1 minus T2, mu R T1 minus T2, and gamma minus 1. Mu R T1 minus T2, initial minus final, gamma minus 1. So this is your work done for adiabatic process. This is work done for adiabatic process. This is work done for isothermal process. Now you look at our graph. This one is isothermal, this one is adiabatic. Third process is again we are compressing, but this is an isothermal one. So this one is an isothermal one, and this is again an adiabatic one. Again we are keeping it on an adiabatic stand and we are compressing further. So this is again an adiabatic case. Now what we'll do, we'll use our isothermal and adiabatic work done, and we'll calculate the W1 and W2. So in W1 only we are supplying the external heat. Here we are not allowing any external heat. W2, the system is releasing the heat, right? And here also there is no business or no external heat is allowed to come in or come out. So in first case and third case, first case we are supplying heat, and third case heat is rejected by the system or released by the system, right? So let's say Q1 amount of heat is supplied, and here Q2 amount of heat is rejected. So this is also work done. That is work done is the heat supplied minus heat rejected. The difference or the amount of heat that is supplied minus rejected, that amount of heat is the work done. So we'll use that. Just I have written that this whatever amount of heat we are supplying, that amount, that heat has done the work, and here whatever amount of work we have done on the system, that amount of work heat has been released. So W1 equal to Q1 we can write, and W1 is your mu r. W1 is mu r, and your temperature is T1, and ln your volume is V2 by V1. Fine. So this is your W1 first case. Now second case, W2 is a adiabatic case, 2 to 3. So here we'll use the adiabatic case, that is W2, which is equal to mu r. You look at the temperature has become T1 to T2, so my formula will become T1 minus T2 divided by gamma minus 1. This is not R, this is gamma, Cp by Cv, right? And this is third, W3 is, here heat is released, which will be equal to your heat released, that is Q2, and the value is mu r. What is the temperature here? Temperature is T2, so mu r T2 ln, and what is the volume? Volume is changing from V3 to V4, but see one thing, here the volume is decreasing, so a negative sign will come up, or we can write down this is V4 by V3, or negative sign if power, it will become -1, so V3 by V4. Are you getting or not? I am still confused, so I can write minus, this is ln V4 by V3 final by initial, or what you can do, if minus, I'll write this power will become -1, so it will become finally V3 by V4. I'm writing directly, so this will become V3 by V4, because work is done on the system in the third process. Now fourth one, that is W4, here work done is again a adiabatic process, temperature becoming T1 to T2 to T1, but it is again a compression case, so minus sign will come up, so it is T2 minus T1, but again you will get a T1 minus T2. I think you are getting, so negative sign will come because it is a compression case. Expansion case, this formula you are getting for expansion case. For compression case, you will get a negative sign, or you can say T2 minus T1. So here final temperature minus T2 means final temperature minus initial temperature basically. So here final is T1, initial is T2, so T2 basically it is T1 minus T2 will be, because negative sign, right? So it will be T1 minus T2 by gamma minus 1. Now you see in third and fourth case, here work is done on the system, you are doing the work on the system. Here work done by the gas is doing work, you are not doing anything, you have just kept the system on the high temperature T1, and you have brought the system and kept it again on a adiabatic stand, so you have not done any work here. Basically the work is done by the gas, so here both the cases work is done by the gas, here work done on the gas. So net work done, net work done is W1 plus W2. Here work is done, a positive work done, that is W2, and 3 and 4, this is work done on the system, so I'll write W3 minus W3 minus W4. Fine. So you see that W2 and W4 are same. W2 and W4 are same, so I can cancel out W2 and W4. So W1 minus W3 will remain. So W1 is what? W1 is mu r T1 ln V2 by V1 and minus W3 is mu r T2 ln V3 by V4, right? So this is your net work done. Now we'll calculate the efficiency. So this is your W net. So this is the net work done by the engine in this reversible process. Now we'll calculate the efficiency of the machine. This is very important, and question many times comes on the calculate the efficiency of the machine. So in this case, efficiency definition we have discussed. So W by Q is the heat supplied, the work done. So in this case, suppose Q1 is the heat supplied, and W will become your Q1 minus Q2, that heat supplied minus heat rejected, that is the work done, and divided by Q1, or you can say this is 1 by 1 minus Q2 by Q1. This is the efficiency basically, right? So Q2 is your W2, Q2 is your W3, and Q1 is your W1, right? So you can divide here and you can calculate efficiency. So what you will do basically, few more steps just I'll do and I'll simplify it. So here Q2, or you can write here, this is 1 minus Q2 is your ln mu r T2, this one ln V3 upon V4, ln V3 by V4, divided by your Q1 is mu r T1 ln V2 by V1, mu r T1 ln V2 by V1. Now mu is the number of mole, r is the gas constant, so cancelled out, and this one we are left with now T2 ln V3 by V4, T1 ln V2 by V1, 1 minus, right? Now I have to get some relationship this ln, so that I'll get a simpler equation. So what I'll do, we know that for adiabatic process, in the last video I have discussed about the relationship between PVT in adiabatic process, and there we got the relationship between temperature and volume. If you remember, the relationship between temperature and volume, that is T V to the power gamma minus 1 is a constant, right? The relationship between TV, that is TV to the power gamma minus 1 is a constant. So we can write, and this is for adiabatic process. Adiabatic process. Now what are the adiabatic process in here in Carnot cycle? So adiabatic is 2 to 3 1 and 4 to 1. So these two are the adiabatic processes. Here adiabatic, and here also adiabatic processes is being done. So now if I'll use this law your equation here, Tv to the power gamma minus 1, so here temperature for this adiabatic is T1 to T2, right? So temperature here is suppose this point, I'll use this equation. So T1, this is V2 gamma minus 1 equal to this position, this is T2 V3 gamma minus 1, because it's a constant, right? Tv to the power gamma is a constant, so T1 V to the power gamma will be a constant, because this is an adiabatic process. So in this curve, any point my equation should satisfy. So I can write this, right? And it's a constant. So I can write like this. This one I'll rearrange, V2 V3 to the power gamma minus 1, T2 T1 I'll divide T2 by T1, right? Or I can write in this way, that T2 by T1 equal to, right? Or you can write in this way, V2 by V3 equal to T2 by T1, 1 by gamma minus 1. Suppose a square is 2, then a equal to 2 to the power half or root 2, right? So power will become reciprocal here, that is 1 upon 2. If it is a square here, so it will become 1 upon 2 here. So here it is gamma minus 1. If I'll write v2 by v3, then the power will become here 1 upon gamma minus 1. Fine, this is simple case. So this one I got one relationship. Let's say this is equation 1. Another relationship I'll get for this one, 4 to 1. So 4 to 1, if I'll use this equation, so T2, so 4 to 1, this case what I'll get, adiabatic case, T2 with V4, T2 V4 gamma minus 1 equal to here T1 V1 gamma minus 1. Fine. So I'll write the same way. So here it will be V4, directly I am doing V1 equal to, sorry, I'll write this term T2 by T1 in terms of T2 by T1. So I'll write this is I'll divide this one here. So T2 by T1 whole to the power 1 by gamma minus 1 equal to V1 by V4. So directly I did the same thing whatever I have done here. T2 by T1 gamma minus 1 equal to V1 by V4. Right. Now here also T2 by T1 1 upon gamma minus 1, here also T2 by T1 gamma minus 1. So this is 2. So from 1 and 2 I can write, so we can write that this volume are same, that is V1 by V4 equal to your V2 by V3. That means if I'll cross multiply, if I'll rearrange it, basically V1 I'll bring here and V3 I'll take here. So it will become V3 by V4. Why I am doing it? I am bringing, this is V3 by V4, right? So I am bringing this term here, V3 by V4 term, so that I'll use my relation of whatever the result I'll get here, I'll use it. Fine. So V3 upon V4 equal to this one will become V2 by V1. So this relationship you see, so V3 by V4 equal to V2 by V1. If I'll use log both side, ln both side, so ln V3 by V4 equal to ln V2 by V1. That means these two things are equal, so cancel out. Now it makes my life easy. So what equation I'll get? Only T2 upon T1 is left out. Once I get V3 upon V4 equal to V2 upon V1, so it cancelled out, only T2 upon T1 left out. So my efficiency will come up, my final efficiency is coming up as eta equal to 1 minus T2 by T1. This is a nice equation. So my machine works in between the temperature T1 and T2, and this is also a definition of Carnot engine, that the whatever engine you take, the efficiency won't increase if it is working between T1 and T2, right? The efficiency you cannot increase beyond that, and efficiency will also be within from 0 to 1, right, or 0% to 100%. So this is your efficiency of your machine, and this is all about your Carnot cycle. It's very important, especially this result is very important. Work done is also very important in entrance in many competitive examination. This question comes from this Carnot cycle, and concept of Carnot cycle, conceptual question along with the numericals also comes from the Carnot cycle. So I hope all the steps in this discussions are clear. If you are still not clear, any step, any doubt, you can write in the chat box. If possible, I'll make another video clarifying your doubts. Thank you. See you again with another topic. Thank you.